So I'm John Rauser, and I'm here from the future. Okay, so I'm not literally here from the future in the science fiction sense. Rather, I'm here from the future in this sense. So I really like this idea. The future is already here. It's just not evenly distributed. So this is an invitation to the first meeting of the Homebrew Computer Club. Gordon French invited people to hang out in his garage in March of 1975 with the goal of making computers more accessible to everyone. In 1975, digital computers had been around for a long time, but what was relatively new was personal computers. This is one of the first personal computers, the Altair 8800. The way you booted an Altair 8800 is you toggled those switches on the front to encode the 16-bit address of a bootloader, and then you toggled the execute switch to get the thing running. This is comically primitive by our modern standards, but the people building their own computers from mail-order kits in 1975 were at the leading edge of the personal computer revolution. They were glimpsing the future that you and I live in today. In fact, Steve Wozniak was at the very first meeting of the Homebrew Computer Club, and he credits that meeting with inspiring him to design the Apple I. And so in a very real sense, there is a direct line between the Homebrew Computer Club and this device, which hundreds of millions of people carry around in their pockets every day. So that's what William Gibson means when he says that the future is already here. Those enthusiasts in 1975 were living in a microcosm of ubiquitous personal computing. Okay, when I say that I'm from the future, who the heck am I? Well, first, I'm a member of your tribe. I spent the first half of my career as a software engineer, including 8 years at Amazon. While I was at Amazon, I spent a long time working on website performance. That work culminated in running Amazon's worldwide website performance program. While I was running that program, the very first thing I did every morning and the very last thing I did every night was look at a set of about 80 graphs, which told me if the site was performing acceptably. If I saw something wrong, I figured out a likely cause and paged people to get it fixed. So I am of your tribe, the people who care about monitoring and metrics and observability. To the extent that I was any good at managing web perf, it was because I loved data. And that's what led me eventually to become what people today call a data scientist. But really, I was a data scientist back then when I was looking at my web performance charts every day and night. I was just looking at data and trying to make sense of it. And you too are data scientists, all of you, though perhaps you don't know it yet. And what I've learned, having made the leap to full-blown data scientist from web perf nerd, is that the data science tool chain is really pretty spectacular. And it's hard for me to say the same is true for the monitoring and alerting tool chain, at least the open source part of that tool chain. Like I use Graphite and Grafana in my current job, and while they are sufficient, they pale in comparison to what's available to me as a data scientist. And so what I want to do today is I want to talk through some of the aspects of the data science toolchain, how it's changed recently, and why I think it's so fantastically powerful. Specifically, I want to talk about R and the Tidyverse. Probably a lot of you have at least heard of R before. If you haven't, R is a programming language designed for data analysis tasks. And R is also a larger statistical computing environment with an extremely diverse library of add-on packages. R has a reputation, somewhat well-deserved, for being a very difficult language to learn. And that's a big part of that difficulty is that while the core of the R language is very small and beautiful, the base R library has what I call PHP disease. There are just a million functions with absolutely no consistency. This is the opening of a book called the R Inferno, which is modeled after Dante's Inferno. So this book tries to explain all of the little gotchas in R. It is 126 pages long, and I have to say it was tremendously useful to me as I was learning R, but things have really changed. R isn't nearly so difficult as it used to be, and that's largely thanks to one person, this fellow, Hadley Wickham. Hadley's a professor of statistics at Rice University and chief scientist at RStudio, a company that makes a really nice IDE for R programming. Hadley is the driving force behind the Tidyverse, which is a set of R packages that share a single, thoughtful philosophy and are designed to work together. In Hadley's words, the heart of the Tidyverse is a set of consistent shared principles that every package in the Tidyverse adheres to. So I'm only going to talk about 2 of these packages, but for people who care about monitoring and operational tasks, they're the most important ones. So the first is ggplot2, which is a package for plotting data. Even if you have never heard of ggplot2 before, you've almost certainly seen plots that were made with it. If the gray background with the white grid lines in this plot looks familiar, that's the signature of a graphic that's made with ggplot2's default settings. And then the other package I want to talk about is dplyr, which is a package for querying and manipulating data. So development on these packages started in 2005 when ggplot2 was released, but it's really accelerated in the past 3 years. And it's in those 3 years that I've really started to feel like I'm living in the future. And so here we come to my thesis. These tools have already had a tremendous impact on how a huge number of data scientists do their work, but it isn't going to stop there. I believe that the ideas in the Tidyverse, not the tools themselves perhaps, but the fundamental ideas that they are built upon, those ideas are going to have profound impact on everything having to do with data manipulation and visualization, or data analysis more generally. And that obviously includes things like monitoring and metrics and analytics, the things that you folks all care about. Okay, so I want to talk about these ideas in the context of a real problem. So we're going to look at some sunspot data. Sunspots are a result of the fact that the sun is a giant ball of plasma, and that plasma is flowing around in super complex ways. People have been observing sunspots for hundreds of years, and so I downloaded a daily sunspot dataset, cleaned it up, made a first stab at a visualization, which looked pretty crappy. The series I downloaded had daily observations, and the lines I used to plot this data are really heavy, and so there's a lot of overplotting. You can't really see the data very well. This sort of problem is super common in dashboards with fine-grained telemetry data. There are lots of ways to address this problem. Here's one. All I've done here is to draw the data as points with no line adjoining them, and then I muted each individual point by making it mostly transparent. And now you can actually start to see the data. So for example, you can see that in the 1850s, the data never takes on values between 1 and 20. In more recent times, it never takes on values between 1 and 10. So it turns out that I'm plotting a metric called sunspot number, which today is defined as the total number of observed spots plus 10 times the number of groups of spots. But it looks like in the past it was different somehow. This is the kind of thing that a visualization makes obvious. Okay, so let's talk about tools. In particular, I want to talk about code versus clicking. So let's go look at some code. So remember this plot. Here's the code that made it. What ggplot2 offers is a domain-specific language hosted in R for making plots. And that language is based on something called the grammar of graphics. That's what the GG stands for in ggplot2, the grammar of graphics. So just to explain briefly what's happening, that ggplot function call is essentially setting up the frame of the plot. I'm saying I want to plot some data that's stored in a variable named sunspots, and then comes something called an aesthetic mapping. That's what that AES function call is. And what I'm saying here is that there's a variable named dt for date in my data set, and I want to put that on the x-axis, and then there's another variable named sunspot number, and I want to put that on the y-axis. Okay, so far so good. I haven't yet said how to draw the data. The way I do that is to add, using the plus operator, a layer where I'm drawing the data as a line. And this code results in this plot. And so something kind of remarkable just happened, and so I'm going to go over that again really briefly. To make this plot, all I needed to do is to specify 2 things. First, I needed to say what was the mapping between variables in my data and aesthetic features of the graphical elements of the plot. And now here I'm only mapping variables to x and y position, but I could map variables to things like color of points, or the size of points, or shape, or alpha transparency, or lots of other things. And second, after declaring that mapping, I need to say what kind of geometric objects should encode the data. Here I chose a line, but I could have chosen points or bars or a surprising number of other geographic elements. And this is the power of the grammar of graphics put into a domain-specific language. This little bit of code, easily small enough to fit in a tweet, this little bit of code completely specifies a plot. But once I saw it, I didn't like the line plot. I wanted to try something different. And so I changed the geometric object representing the data from a line to points. And then to mute the visual impact of each point, I added some parameters to make them small and mostly transparent. And so you can now see something only when there's lots of points that stack up. And so now I have this nice plot with less overplotting. And so far, you might not be very impressed. You might be saying, well, why is this any better than a tool like Grafana, right? Where if I want to change from showing the data with points instead of lines, all I need to do is click a checkbox. In fact, you might say it seems worse because I have to do all that typing and I have to remember the syntax, and that's really annoying. But what about when you have 5 or 50 plots and you want to make the same change to all of them or to all but one of them, right? Now you're in an endless hell of clicking so painful that you probably just won't do it. You'll just suffer with whatever you've got so far. But recall that ggplot2 is a domain-specific language hosted in R, and so I've got all of the features of a general-purpose programming language available to me. And that means I can give those constants names, and then use those names not just in this plot, but in lots of plots. And if I ever change my mind about those values, then I change them in one place and not in dozens. But it gets better. A plot like this is an object in the language, and so I can give that plot a name, like P, and then I can take a shot at guessing the structure of the cycle. If we eyeball this, it looks like maybe there's a cycle that lasts about 11 years, and there's a minimum in roughly 1954. So here's a really grody line of our code that computes an array of dates. You can see that 1954 and the 11 years lurking in there. And now because I'm working with composable objects in a programming language, I can add a layer of vertical lines to the plot and get this, where the blue lines are equally spaced every 11 years and they kind of sort of line up with the troughs. So the first thing that I want you to take away from the data science toolchain is that what ggplot2 offers is the ability to express visualizations completely in code, no clicking. But completeness isn't enough. Right? A library like D3 in JavaScript is complete, but the equivalent code for this line plot in D3 looks like this, right? So I had to shrink the font size down to 6 points to get it all to fit. And so not only is ggplot2 complete, it is also compact and expressive, which makes it extremely powerful. I've only shown you the simplest possible plots, but for almost any plot you can imagine, including plots that don't have names today, you can go from an idea to a realized image in a handful of code faster than in any other language I'm aware of. And because of this, ggplot2 has already transformed the workflows of many data scientists, and it's not going to stop there. I believe that the ideas in ggplot2 and in its successor, ggviz, are going to transform every tool that deals in statistical graphics, monitoring tools included. If you want to learn more about ggplot2, you can take a look at Hadley's book, R for Data Science, which is available online for free at that link right there, or you can buy a copy from the nice folks at O'Reilly. Okay, the next idea I want to talk about is another idea from R, the data frame. So the data frame is this fantastically useful idea that hasn't been copied nearly as widely as it deserves. At its core, a data frame is just a table-like structure. You can think of it like a spreadsheet in Excel or a table in a database. A data frame is a structure where there's one row per observation and a column for each variable. And you might wonder why this is such a great idea. After all, you might say, well, hey, my language has two-dimensional arrays, or my language has lists, and I can make lists of lists. The power of a data frame is really in the interface. The key idea in a data frame interface is that data alignment is intrinsic to the object. And that mainly means that a row of data will remain intact through any operation. And to see why that matters, maybe you've had this happen to you in Excel, where you go to sort your data, but oops, you've accidentally selected a single column instead of the entire table, and now you've wrecked the alignment of your data. Another nice feature of a data frame is that columns and optionally rows have names, which allows for very natural indexing and filtering, and it also makes it super easy to support joins. But the killer feature of a data frame is that they are a very flexible structure that can accommodate the needs of the vast majority of analytical problems. And what that means is that people writing libraries in R can assume that you'll pass in a data frame and that they can return results back in a data frame. And the power of that is it allows you, in Hadley's words, to solve complex problems by combining simple uniform pieces. A data frame is the uniform medium of communication between tools in R. In this way, you can compare data frames to Legos, right? What Lego provides is this consistent interface, and perhaps surprisingly, that simple interface allows the expression of fantastically complex ideas. You see these ideas show up in monitoring tools, right? In Graphite, functions usually take and return a series or a series list, and that makes it easy to chain together a bunch of functions like this. I think that this one feature of Graphite, of its design, is a major reason for its popularity. And in a way, a series list is a bit like a data frame, but R goes one further. R supports something called a nested data frame. So you're used to tables containing atomic data types, like numbers or strings or Boolean values. But in R, a data frame can be a list. And an R list can contain any object you like, including another data frame. So to see how that works, it's probably easiest just to look at an example. So here's a data set from the Gapminder tool. It has demographic data for different countries over time. And what I can do with this in R is group that data by country and continent, and then ask it to nest the remaining columns, the demographic data. And so now what I get is one row for each country, and the last column contains tibbles, which are a special kind of a data frame. Each one is 12 rows long and 4 columns wide. And so what's happened is we've nested little data frames in each row of the larger data frame. And you can find something like this idea in some monitoring tools, like in Cakewolf from Circonis, where they have the notion of a histogram data point, which feels, I have no idea how it's implemented, but it feels to me like a data frame where one column is a timestamp and another is a histogram object. But if you go all out and allow the nesting of data frames inside data frames, then you take an already very flexible structure and you make it even more flexible and useful. And so I think that nested data frames is an idea that monitoring folks should just steal outright from the data science community. Okay, next I want to talk about calling functions. So I mentioned that since Graphite has this uniform structure of a series list, and because each function takes a series and returns a series, it allows the chaining together of functions like this. But chains of functions like this are hard to read because you have to read them inside out. You have to spend a lot of time carefully matching up your parentheses. I want to talk about two different ways of calling functions. And the first is to just give a name to every intermediate result. But naming is hard, and so we usually end up with something awful like temp or foo. The truth is that often these intermediate results aren't actually very interesting, and it's not worth coming up with good names for them. But there's another way, but this way is much more readable than the first way, than those nested function calls. But there's another way to call a series of functions, and that's with a pipe operator. So that funny % greater than % operator in R is the pipe operator. The R language has really nice metaprogramming features, and so that operator is just a function that calls the function on its right-hand side with the result of evaluating its left-hand side. In other words, these two snippets of code are identical, but the first is just a lot easier to read. You can read the pipe operator like the word then. So the first we say, please scale the data, and then compute a percentage, and then take a moving average, and then alias it. You're probably all familiar with the pipe operator in one of my favorite data analysis environments of all time, the Unix command line, right? It's worth noting again that this works so well because every tool in the system reads and writes a flexible common format, the text file. And so you can combine simple tools to solve complex problems. The Grafana UI emulates a pipe on top of Graphite's language, so you can read these left to right. First scale to seconds, then take a moving average, then apply an alias. Circonis' Cakewolf language has a pipe operator as a first-class citizen. So let me show you a realistic example of using the pipe operator in R. Remember that we had the sunspot data where we had a guess at this 11-year cycle. Let's try to fit a real time series model to this data. To do that, the first thing I might want to do is to reduce the granularity of the data set. The raw series is daily, which is way more data than we need for a signal that moves as slowly as this. And so let's transform the daily series into a monthly series. Here's code that does that using dplyr. Dplyr is another part of the Tidyverse. It's a domain-specific language for data manipulation. So like ggplot2, it's expressive and powerful, and I can only give you a tiny taste for it here. But if we read through this, we see that what we're doing is we're starting off with the raw daily sunspots data, and then the first thing we do is mutate it, adding a column named month, which just holds a string representing the month that the day fell in. And then we group by that new month column and apply the summarize function to each group. Summarize will return a data frame with one row per group and add a new column, which is the average sunspot number for that month. And if you know SQL, this all sounds very familiar. This is exactly like a group by with an aggregate. But it's worth noting that unlike SQL, I don't have to aggregate a group, each group into a single row. The functions that I apply to each group can return one row or 0 rows or more than one. In fact, dplyr can do anything that SQL can do and a whole lot more. Dplyr is so powerful and expressive that in the fullness of time, I expect the ideas in dplyr to displace SQL-like languages for analytic work. So here's a plot of that new monthly data with a smoother laid over it. It's worth noting that ggplot2 has really nice smoothing features built in, and so to add that smoothed line, all I did was add another layer, again with the plus operator, with a couple parameters specifying the smoothing algorithm and how much to smooth the data. Okay, and then just to finish up, I said we wanted to fit a proper seasonal time series model to this data, so here's code that does that. The details of this model are not very important. What I'm doing here is I'm pulling out that mean sunspot number from my data frame, and then I'm fitting a TBATS model to it with a seasonal period of 11 years. TBATS is like a fancy version of Holt Winters, if you're familiar with that. And then I can take that model and I can plot it like this. And so at the top, you can see the original data. At the bottom, you can see the model's estimate of the regular 11-year pattern. And in the middle is a sort of a seasonally adjusted level of sunspot activity. This is not a good model. It turns out that the solar cycle is actually super, super complicated. It's not like a clock running on an 11-year cycle. But this was just the fun first shot at like taking a look. Okay, so to recap, at the core of what makes modern R such a great data science environment are a couple of fundamental ideas. First, the data frame, which is a very flexible container for data that allows nesting of data to arbitrary depth. And second is this tool called dplyr, which is a domain-specific language for data manipulation hosted in R that, on top of being expressive and powerful, lets you write very readable code because of its support for the pipe operator. Together, these tools help achieve Hadley's goal of allowing you to solve complex problems by combining simple, uniform pieces. Okay, so at this point, I hope I have some of you thinking, hey, I want to live in the future too. If you want to start playing around with these tools and the larger ideas, I'd say it's really worth it to teach yourself to use R in the Tidyverse. It is a fantastic tool for data-intensive problems like capacity planning or modeling dependencies in complex systems. There's also a thing called Shiny, which is a web application framework that you can probably use to replace your existing dashboards with something a lot more powerful and flexible. I should say here, I don't work for RStudio. I'm just a super happy customer of their products. But my real goal with this talk is to inspire tool makers as much as users. I want to end by looking at how Hadley did what he has done with the Tidyverse. I want to talk about programming as a way of thinking. So I got started thinking about this after I read this really great piece by Alan Downey in Scientific American. It wasn't until after I read this piece that I began to understand what Hadley had done with the Tidyverse. So the argument that Alan Downey makes is that modern programming languages are so powerful because they are very close to both the way that you might describe the concept in natural language and in formal, more mathematical notation. So there are really three different languages, he argues, when you work, that you work in when you work with computers. There's the ideas that are running around in your head in natural human language. And then there's something akin to math, a formal algorithm or a description of the problem. And then there's code in the programming language. And Downey points out that we are limited to the subset of programs that we can express in all three of these languages. And he takes pains to point out that it's what we can express, not what can be expressed. Like theoretically, you can express any idea in a general purpose programming language. But we, it turns out, are the weakest link. We are limited by our ability to handle complexity. And how do we handle complexity? We break the program into pieces, and the larger the program, the more it has to be divided. In this essay, Graham talks about 2 different ways to do this. You can design either top-down or bottom-up. Top-down, you are certainly familiar with. You say, hey, my program has to do 4 things, and so it'll have 4 subroutines. And then you look at each one of those subroutines, and you split them up into some smaller pieces, and you keep doing that until you get a tractable idea that you can implement in a handful of lines of code. So bottom-up design is different. In languages like Lisp and in R, you don't just do top-down design. You also have the power to build the language up toward your program. You think, I wish R had a pipe operator, and then you just go and write one. You can do this because Lisp and R have strong metaprogramming features. The language allows you to operate on the language itself. And when you do this, Graham uses this lovely metaphor to describe the result. Like the border between 2 warring states, the boundary between language and program is drawn and redrawn until eventually it comes to rest along the mountains and rivers, the natural frontiers of your problem. In the end, your program will look as if the language had been designed for it. With ggplot2 and dplyr, Hadley has built the language up to the problems of data visualization and manipulation to the point that you can do practically anything you desire with small and beautiful code. And the ideas in the Tidyverse are so good that I can't imagine them not leaking out into other tool chains. And so you should look at the Tidyverse because Hadley is thinking more clearly about tooling around data than anyone else. And if you do look at the Tidyverse, I think you'll be inspired to make the monitoring toolchain better. That's all I have. Thanks for your time.